All right, we're gonna continue on here. Last time, pretty much we finished up chapter 14, perhaps. We talked about obviously three different titrations and titration curves. Uh, we had our strong acid, strong base titration, where again, we have our equivalence point there should be 7, as we have a neutral salt at that point, and that's the only thing left. We had our titration curve, which is kind of similar, and of our weak acid and strong base titration. Here again, because at the equivalence point there, it should be basic, because we will have a salt that came from a weak acid, which will go through hydrolysis and act as a base and accept the H plus from the water as it goes through that hydrolysis, creating hydroxide. We finished up talking about kind of the upside down one there. So, and volume of acid. This is a strong acid, weak base titration. And here we're adding actually the acid, so the pH is actually decreasing. The same idea here, we would expect the equivalence point to be acidic, as we will again have a salt at equilibrium, or the equivalence point, that will go through hydrolysis here. And because it comes from a weak base, it will act as an acid. It will donate an H plus over, and again, we'll make H3O plus in that reaction and become acidic. So as we talked about, it's important to know what type of titration you're doing. It's also important to know really where you're at in the titration curve, because as we talked about, really you could sort of know the calculation you should be doing before you actually do the calculation. So again, that kind of makes it hopefully a little bit easier along the way. Any questions on any of that calculations we did there? All right, so just to finish up this chapter, we're going to talk a little bit about indicators, and we kind of talked about it as we were kind of going through. But acid-base indicators are essentially weak acids. They have a protonated form, which means they have the hydrogen on it. They have a deprotonated form, which means they have lost that hydrogen. And really that ratio of kind of protonated to deprotonated form you see will kind of determine what color you will see. An indicator, again, works over a specific sort of pH range typically. And again, usually it will change from kind of one color to the next, and maybe a few colors along the way. And ideally, the purpose of the indicator, obviously, in a titration is to tell us that we should probably lay up our titration and stop at some point, as we are reaching the equivalence point. So when you're choosing a indicator to use in a titration, you clearly want one that's going to actually change color somewhere near your equivalence point. And depending on what type of titration you're doing, as to what indicator might be good. So again, you can see here, crystal violet goes from kind of yellow to green to blue. We have something like our phenolphthalein down here at a pH of 8, kind of colorless, to again a darker pink color along the way. Dare I say, I think that's the one we use in lab, I feel. As you saw there, you started yellow and then again went to that minty color and then to our bluish color. And obviously you also tossed in there perhaps some phenolphthalein, which made kind of blue and pink, a pretty purple there at the end. So they have a specific color in the sort of acidic solution and a color in the basic solution. And again, although on this map it doesn't really show it, but that if it's below sort of the pH of that indicator, it will probably be that first color that you see there, even if it's not specifically at that sort of pH range. So why don't you take a look at one here, and again, you can see in our table of some indicators in the pH ranges which they work over. So for a titration of HNO2 with potassium hydroxide, which indicators from this list would be good ones? So take a moment and kind of think about titration and think about which ones here would be pretty good choice, perhaps. Okay, so in this case, what you probably want to think about is what type of titration you're doing. So hopefully you know HNO2 is what type of acid? As a weak acid, right? And KOH is a strong base. So this is the titration you're doing. It's going to give you a wonderfully drawn sort of curve like so, maybe. That means that in this particular case, as you reach the equivalence point, you once again will have a salt there that will go through hydrolysis. And because, again, that salt comes from a weak acid, it will really be this guy here doing a little reaction with water there, and it's going to accept the H plus. And in this particular case, we will get our HNO2, and we will make some hydroxide here. And that's quite important because that would mean we would expect the equivalence point here to be basic, right? So when we're choosing an indicator, we clearly would not want an indicator that changes color before basic. So looking at our list here, clearly this is probably not going to be a great choice as it's going to change way before you get to the equivalence point. So it's going to do you no good. Same thing, same thing. Same thing, same thing. Here you might think it might be okay, but again, 7.6 is not very deep into the basic, and probably at that point it's already changed color, so it's probably not going to be so great. So really our creosol red does get into some basicness there, which is good, and also our phenolphthalein. So probably these two right here, because we do see a color change there in the basic sort of pH, would be a really good choice for that. Clearly, if we were doing, say, the other titration there that we talked about at the end, which was like our HCl and our something, not that, ammonia, that's what I was trying to spit out there. That is going to give us at the equivalence point a more acidic pH, and obviously you can choose more one that would change in the acidic range. You could also do a quick calculation, right, based on what you're titrating and figure out what the pH should be at the equivalence point. Again, you could really sort of narrow in on an indicator that would work really well. Any questions on that there? All right, well, they say that is chapter 4 has a title somewhere. Maybe. There it is. So not much of a title, but chapter 15 is sort of a short chapter, but a lot of stuff packed in there. The good news is we are on the downhill swing of our hard stuff, I suppose, ish. So we're on the downward cycle here on chapter 15. A couple of things we're going to talk about is some more K values because we have not done enough of those. So we're going to do KSP in this chapter. KSP is the solubility product. And we will also talk about KF, which is the formation constant. And that is for really complex ions. That's where we usually see those. So we're going to start with KSP and solubility equilibrium. So if you remember solubility rules, maybe, you know, things like group 1 is soluble in everything. Things like chlorides, bromides, and iodines are also soluble in everything except for group 1, which is lead, right, mercury, and one of those other ones I can't remember right now, but silver sounds good what I'm looking at. So those are, you know, some rules that would probably be helpful for you in this chapter. The good news is if you don't really know your solubility rules, there's other ways to figure things out, but it might not hurt to sort of look at it. And one of the things that sometimes people misunderstand about solubility rules is they have that table or maybe how to memorize that table, whatever it may be. And they think that it is always 100% going to happen that way, and that's not always the case. And what I mean by that is even if solubility rules, for example, say that something should make a solid, there is a lot of factors that actually come into play as to whether or not, for example, you would see that solid actually form, some of which we will talk about in this chapter. Things like pH is a very important factor, things like concentration of the ions, and things like common ions being present as well. Now, even something that is technically insoluble, like our friend right there, silver chloride, Even things that are insoluble actually do have some degree of solubility. It's just super, super small, which is why we consider them being insoluble. So even if you have something like silver chloride in solution, it actually will set up an equilibrium. And that is silver chloride would go to our silver ion and our chloride ion. And since that's an equilibrium, I feel like we could write an equilibrium constant for that. And that's going to be our KSP, which would be the concentration of silver times the concentration of chloride in this particular case. This is again what is known as the solubility product. Now, when we talk about the solubility product in the KSP, they are equilibrium constants for things that are typically insoluble. So these are basically equilibrium constants for things that when you think about sort of the solubility rules, you would normally say are insoluble. Because they are normally insoluble, that means that they typically have a very small value for the KSP. And how all these reactions are written or equations are written for KSP is always like this. Solids on the left and your aqueous ions are basically on the right-hand side. And because they are really, really small values, typically KSP, that means just like any other equilibrium constant, if you have a small value of K, you pretty much have reactants, and that is why we consider these things still insoluble. And by small, as we will see shortly, like to the minus 34 or something like that. So very, very small values. So that's why they are considered pretty much, insoluble. But again, it also demonstrates that even something that is insoluble can actually sort of break apart a little bit, very, very small amount. We write the KSP like this, which is typically always going to be our product side because on our reactant side, it is always solid. So just like normal, we don't include solids in our equilibrium expression. So usually when you look at a KSP sort of expression, it really is just what's on the product side. And we do the same thing we normally do. If there is a coefficient, we still need to take it to the coefficient. Same thing here, a 2. And same thing here, a 3 and a 2 as well. Now, one of the things we can use KSP to help us understand, as we'll talk about, and also another letter that we've seen earlier on as well, which is Q. Q is the reaction quotient. If you remember, we used it earlier on to figure out whether or not a system's at equilibrium, and if it's not at equilibrium, really which way it needs to go to reach equilibrium. So we could actually calculate Q and compare it to the KSP. And once again, just like earlier, Q would be calculated the same. I guess we'll put it this way. It's calculated the same as the KSP, so those products basically. If you calculate Q and it's less than the KSP, then you will have an unsaturated solution. And an unsaturated solution, right, is a solution that has not hit the maximum amount of solute that will dissolve at a given temperature. So pretty much everything will dissolve, and you would not expect a precipitate to form. If you calculate Q and it is equal to the KSP, then you are at what is known as a saturated solution. And the definition again of a saturated solution is the point where you've hit the maximum amount of solute that will dissolve in a solvent at a given temperature. You're pretty much right there at, if you add any more solid at that point, no more is going to dissolve, right? So that will give you really the next sort of thing there on that table, which is if you calculate Q and it's greater than the KSP, you will have a supersaturated solution, which means that solid is not going to stay dissolved. It's going to come out of solution basically, and you would expect a precipitate to form. So because, again, these reactions or equations are usually written solid to aqueous ions, once again, if you write the Q on the left and K on the right, it goes opposite of where that thing is pointing. So again, unsaturated would mean it would go towards the product side. Aqueous, no solid. Q is greater than K would go towards the reactant side. And again, you would see a solid or a precipitate sort of form. Any questions on that there? So here's a table which you clearly can see, or maybe I'm gonna say. Again, you can see if you just kind of look around, there's a lot of really, really sort of small values here, -38, -48, -45, even -12 and 9. They're pretty small sort of values. So again, KSP values are typically for things that are insoluble. And again, that results in a very small value for the KSP as we go through here. So when we have a KSP problem, there's usually kind of two things you're maybe looking at in terms of solubility. And one is what is referred to as the molar solubility. And the molar solubility is really just the molarity. So it is the number of moles of the solute that can be dissolved in a liter of solution. Then you have kind of the solubility in grams per liter, and that is basically the number of grams you could get to dissolve in a liter of solution, saturated solution at that point. Now, depending on what type of problem you are doing, you may need to do an ice table or may not need to do an ice table or may just want to do an ice table for both of them, regardless. So if you are given the solubility of the compound, you want to figure out the molar solubility, which is the molarity of each of the ions present. And from that, you could actually calculate the KSP for it. So one type of problem for KSP is where they don't give you the KSP, but they ask you to actually solve for what the value of it is. The other type of sort of problem where you definitely should do an ice table is where they actually just give you the KSP or don't give you the value. You can go find it in a table. And that's pretty much all the information you're given. You're just like, hey, what is the solubility of this guy? And that's it, basically. And in that case, you actually do an ice table and you would solve the ice table, and that would get you your molar solubility, which then, if you wanted to go from molar solubility, which is moles per liter, to just solubility of grams per liter, what is the thing that kind of ties that calculation together? It is the molar mass, yeah? Perhaps. There you go. So the molar mass there from the periodic table is what ties that together in case you need to go from one to the next. You can multiply the molarity by the molar mass and get the grams per liter, or vice versa. You could divide the grams per liter by the molar mass and you'll get the molarity back of it. So that's a common sort of conversion that's used in these type of problems. So let's take a look at one here. The solubility of silver phosphate, Ag, dramatic pause space there, 3PO4 at 25 degrees is 1.6 times 10 to the minus 5. We're looking for what is the KSP for silver phosphate. So I'm going to show you how to do this, and I'm going to use an ice table, which really you don't necessarily need to use an ice table, but it is kind of helpful to do because there is a lot of calculations in this type of problem where people get confused by, I kind of cubed the thing. Do I still need to multiply it by 3, or I multiply it by 3? Do I still need to cube it? So sometimes just doing the ice table, you can visually see kind of what you need to do, when you're looking at it. So the first thing we want to think about is if we're looking for a KSP, by the way, that's a big hint. If you're not sure, that's probably a solid. So again, if you don't know, that's probably going to be a solid. So we'll start with our silver phosphate, and we're just going to break it apart into the ions. And in this case, we would get 3 silver ions, and we would get a phosphate as well here. Now we're going to do an ice table like normal, except we are going to use, perhaps, dare I say it, a different letter as we do these ice tables. I know, but it'll be all right. So here with the solid, right, it's not really included. So like normal, probably not going to worry about it, put a number or anything like that. So just like normal, we're just going to start with zeros kind of on this side. The change here, again, is going to be minus x on the left, but again, it's a solid, so I'm not even going to worry about putting anything there. And this will be plus, and again, 3. And we actually do not use x here. We actually use s. And that would be plus 3s, and this would be plus s. And the S is equivalent to the X that we've done in the previous table. S here does stand for the molar solubility, which again is, I guess, a fancy way of saying molarity, basically. So very common in these sort of KSP type problems. We don't use X. You could still use X if you like X better, I suppose. But we do use S. And again, that S actually stands for the molar solubility. We'll do what we normally do down here, which is this is going to give me 3S and S in this case. Yeah. Now, when I am ready to put this into my KSP expression, my KSP expression is going to be our product here, which is our silver. Once again, we do need to cube it because of the coefficient, times our PO4 3-. So just like normal, we would take these guys, right, and we would drop them in. And this will give me 3s cubed times S equals my KSP, which obviously in this case I do not have. First off, any questions so far? All right, and again, this is why, for example, I would perhaps recommend still doing the ice table for this one, even though technically you might not need to do it. And that's because it's very common. People will, like I said, kind of put the 3 here, but forget to do the cubing part or do the cubing part and not the 3 part. So that's kind of an important thing to know. What we do know, though, is the solubility of silver phosphate was given to us, which is our molar solubility, and that was 1.6 times 10 to the minus 5 molar. And that means that actually we could just plug that right into there, and that would give me 3 times 1.6 times 10 to the minus 5. Once again, we're going to cube it. And we're going to times it by 1.6 times 10 to the minus 5 as well. And here we will get something. 3 times 1.6 to the minus 5. We're going to cube it. Why not? Let's cube it there. And times it by 1.6 to the minus 5. Going to give us a 1.8 times 10 to the minus 18, I think is this, right? 18. It's a relatively small value for KSP, which we would kind of expect in this case. First off, any questions on the ice table? Now, I said earlier that, whoops, go back. I said earlier that you might not need to actually do an ice table on this particular problem. And that is true if you understand molarity and concentration and how it works when something breaks apart. So for example, you could have, and it's kind of the same thing as doing the ice table, except, hopefully you won't miss too much if you just kind of jump this step. So if you had this guy, as we talked about a second ago, and then we've got 3Ag plus and PO4 3-. And if you know the concentration of the whole thing is 1.6 times 10 to the minus 5 molar, you could do a 1 to 3 relationship in terms of the concentration, and you could times it by 3 and get the silver concentration and see it's a 1 to 1 relationship. And that would give me a 1.6 times 10 to the minus 5 molar for the phosphate. And at that point, you could actually just go right into your KSP expression in this case, and you will basically get it. Now, it's basically like the ice table, except the ice table might remind you to actually do the multiplying by 3 and do it incorrectly. But again, if you understand molarity and how it works through the ions, you could kind of leapfrog it and just go right into it. But again, perhaps the ice table is a safer way to go if you need to. Any questions on that there? Yeah. So it's telling you, for example, when you look at, and we'll do a couple more examples, which might answer your question a little bit more, but what it's basically telling you is you could use it to figure out, how much of this guy you could get to actually dissolve, like in a liter solution at normal temperatures, right? There's other things that you can use KSP for that we'll also talk about, for example, like what you do with qualitative analysis experiments. You could use it to your advantage to selectively precipitate out one ion that's floating around while leaving all the other ones still floating around. So you could use it for that sort of purpose as well. And we'll do some examples actually as we go through it. But something like this, for example, when you see that molar solubility, basically you could also convert it to grams per liter and know that's basically how many grams you could dissolve at normal temperature in that solution. Yep. Other questions? All right, why don't you try one here, which is, what is the solubility of silver chloride? The KSP here of silver chloride, 1.6 times 10 to the minus 10. Some numbers that might be helpful. Silver's molar mass from the periodic table is way over there. Was that 10? Ag is, was it 10? I was going to go for that, sort of. 7.9, we'll go with. And chloride there is 3545. There it is. All right, so we're looking for how many grams per liter can we dissolve of some silver chloride here at 25 degrees? I'll give you a hint. You do probably need an ice table on this one now. Okay, so let's take a look. So in this case here, we have silver chloride. Again, once you see the KSP, you should know basically it's solid, and that is going to give us our sort of reaction, if you will. Again, solid always on the left-hand side of the arrow, and our ions that it sort of breaks apart into on the right-hand side here. That is going to give us a KSP expression of silver times chloride in this case, and this is going to equal 1.6 times 10 to the minus 10. Again, here we have really nothing given to us other than the KSP, which you might also have to look up in a table. So we will roll an ice table here. So 0, 0. Change here going to be plus S and plus S. Again, same way as we would do X's. At equilibrium, we would have S and S in this case. Again, the S is the molar solubility. Any questions on that so far? Just like we do with X's, we're going to slap that back in there. And that's going to give us basically S squared is equal to 1.6 times 10 to the minus 10. A little square root action on both sides there going to get us here, dare I say, a lot of zeros. 0.0000126 as our S value in this case. If I didn't lose a zero along the way, hopefully, 2, 4. That is, by the way, that value right there, that would be the concentration or the molarity basically of chloride floating around at equilibrium. That also would be, as you can see, the concentration or molarity or solubility of silver ions floating around at that way. By the way, that is also the molar solubility of silver chloride, the whole thing together. As if you go backwards, it's a 1-to-1 relationship, so it would be the same number. Basically, when you solve for S in this table, that is the molar solubility of the whole thing, pretty much. And it may or may not be the solubility of each ion like it is in this case. But again, if something had like a number in front of it, like a 3S, you would have to multiply it by 3 to get the concentration of those guys at equilibrium. First off, any questions on that there? We are interested, though, in grams per liter. So this is basically 0.0000126 moles of silver chloride per liter. We need the molar mass here, so we'll do a little addition of those two numbers there from the periodic table and punch it in right would help as well. That's going to give me 143.4 grams per mole. We will use that as our conversion factor here. Moles on the bottom, 143.4 grams of silver chloride up on top. And that is going to get us here, wherever it went. There it is. 0.0018, now we'll go 1 grams per liter of silver chloride. So this calculation right here tells us how many grams of silver chloride we could get to dissolve in 1 liter of solution, or 1,000 milliliters. That is essentially, you could get a whopping 0.002 grams of silver chloride to dissolve in 1,000 milliliters of water. Is that a lot? That is not. That's why we consider silver chloride to be insoluble, right? So you can't get a lot of it to dissolve. Most of it is not going to dissolve. It's going to stay as a solid. So that's one of the things you could get from something like the KSP, is you could know the actual solubility, or how much you could get to dissolve at a particular temperature. Any questions on that one there? All right, let's try another one here, maybe. Calculate the concentration of aluminum, dramatic pause again, +3 there, in a saturated aqueous solution of aluminum hydroxide. We'll move the 3 over a little bit. The KSP here is 2 times 10 to the minus 32. So why don't you give it a go and see what you end up with here. Okay, so let's take a look here and see. So once again, we've got a KSP here. So usually with the KSP, we do want to do an ice table. Also tells me perhaps this guy is solid. So I'm going to write my little equation here, where it is breaking apart into some ions there. 3 hydroxide action happening. That's going to give me a KSP of our products there, which is our aluminum, our hydroxide. Once again, we do need to cube it, and that is going to equal our 2 times 10 to the minus 32. So again, we're going to do an ice table zeros. We got a change, going to be plus S, again, plus 3S because of the coefficients. That's going to get us at equilibrium here, a S and a 3S. Any questions on the table here? This is going to go into our expression there. So that's going to get me an S times a 3S. I got to still cube it. Again, that's a very common error, and why, again, the ice table is sort of helpful for that, hopefully. That is going to equal 2 times 10 to the minus 32. That is going to clean up here on the left-hand side. So we want to do it this way. That's going to give us an S there. We want to make sure that we actually do the next part correctly. That is going to give me a 27S cubed. I can't tell you how many times people just cube the S and forget about the number. Yes, so that's a 3 times 3 times 3 action there, which is 27. That is going to give me 2 times 10 to the minus 32. That's going to give me a 27S to the 4th. Sounds like fun math here. Here we go. All right, so I'm going to divide myself a 27 to the other side. And that's going to get me S to the 4th is equal to 7.407 times 10 to the minus 34. I need to take the 4th root there of both sides. And that is going to get me something, careful on my calculator here, if I could find my button I want. I think I want that one. I'll try that one. 1 divided by 4. That's going to get me a little scientific notation action, 5.2 times 10 to the minus 9 molar. Again, if your calculator is not in scientific notation, you probably got a bunch of zeros and a 5 at the end of your calculator, and that's okay. By the way, if you're not sure how to do that move I just did there, there's 2 ways you could do it. If you got a handy dandy calculator with one of those buttons, you could hit 4 and then that button, and that'll do the 4th root for you. If you don't, you maybe got a button like a caret or something like that, or 10, or not really, something to the x, like x to the something there. You could do parentheses 1 divided by 4 when you take it. So you could do something like 7.407 times 10 to the minus 34 to the 1 divided by 4. That will give you the 4th root. Do 1 divided by 2, it gives you the square root. Do 1 divided by 3, it gives you the cubed root. So you take it to the power button and do parentheses 1 divided by 4 if you don't have that type of button on your calculator, which you might not. Any questions on that one there? By the way, to answer the question, which is here, there it is. That number would be obviously the concentration here of our aluminum would be equal to S, which would be 5.2 times 10 to the minus 9 molar. By the way, if I want the concentration of my hydroxide, what do I need to do? Yeah, because it is 3S here at equilibrium, so it would equal 3 times 5.2 times 10 to the minus 9 molar. And for fun, what would that be? I don't know. It'd be something. 1.6 times 10 to the minus 8 molar in that particular case. By the way, that would mean that you could calculate the hydroxide concentration. You could also get the POH and then the pH. Any questions on that there? All right. So again, make sure you don't forget a cube, for example, and you also make sure that you do know how to kind of punch in those kind of roots into your calculator, because you will get a bunch of interesting ones in this chapter. Yes. Any questions along there? Okay. All right. So let's talk about using the KSP values. So another sort of thing that you can sometimes do with KSP values is you could use it to help you determine the solubility of a group of insoluble sort of compounds. So you can, in certain cases, use the KSP value to compare which one might be more soluble or which one will be less soluble. So remember that if we have our reaction like it is normally written with these guys, which is basically soluble over here, solid to the left, when we look at KSP values, again, the larger the KSP value, that would mean we would actually have more products and it would be more soluble than something with a smaller KSP value. Smaller KSP value is the same thing as a small K value. We would mainly have reactants, which means it would be less soluble. Now, there is a sort of asterisk note on that, which is you can only compare and use the KSP values if you are comparing between compounds that basically produce the exact same number of ions. So that is the only time that you can use the KSP value to sort of make that comparison, is if those things break apart into the same number of ions. Like the example here, that is silver iodide, which will break apart into a silver ion and an iodide ion. That is 1, 2 ions there. We take our copper 1 iodide, going to break apart into a copper ion and an iodide ion. And that also is 2 ions. And if we take calcium sulfate, it will break apart into a calcium ion and a sulfate ion, which is also 2. So this is what we're talking about. Each of these guys break apart into the same number of ions, which means if that is the case, you can use the KSP value to determine which one should be more soluble. That would also allow you, if you had like a mixture of those ions floating around and you're adding a common precipitating agent, like you do in like qualitative analysis experiments, you could determine which one should come out of solution first and which one would actually stay in solution and float around a little bit longer. Now, if you are comparing things that actually do not form the same number of ions, you do actually have to do the calculation. So, for example, if we take these guys in comparison, this is copper 2 sulfide, and that's going to give you a copper 2 ion and a sulfide ion. That is 2 ions there. You're going to take your silver sulfide. That's going to give you 2 silver ions and a sulfide ion. That is 1, 2, 3 ions there. And lastly, if you take your bismuth there, Bi2S3, and broke it apart, You're going to get a couple of Bi 3 pluses and 3 of the S2 minuses. That is definitely like 5 ions there. Now, if you were, for example, to go to a KSP table and look those 3 guys up, you would see these values given to you. And what you would actually see is the copper 2 sulfide has the larger KSP value. The bismuth guy there has the smallest. And if you went solely based on KSP value in this case, you would say that this guy is more soluble because it has a larger KSP value. And you would actually be incorrect in this case because, again, they do not break apart into the same number of ions. That's important because if they do, they basically are going to do the same calculation, right? So if you got 2 ions, you're going to square root it, basically. Which is basically what, where did I pass that thing? Right around here. So you would do the same sort of calculation depending on the number of ions for each of them. So you can kind of compare apples to apples. When you actually do the calculation, what you actually see is the opposite. The copper 2 sulfide actually is the least soluble. And this one down here, the bismuth guy, is actually the more soluble one. So if you're comparing things that are breaking apart into different numbers of ions, you have to do a calculation like we just did in those previous examples with an ice table and calculate what the actual molar solubility is. But if you're comparing 2 things or 3 things that do break apart into the same number of ions, you can actually go by the KSP value. Any questions on that there? Yeah. No, just the total number, because math-wise, it'll come out the same. So again, if it breaks apart into like 1 and 1, you're ultimately going to have 2 ions, which will give you the same sort of math. And it doesn't really matter which, if you had like 2 and 1 or 1 and 2, it will kind of come out the same mathematically wise. So it'll be okay. It's really the total number of ions that they each break apart into is what you want to look at. Other questions? All right, so we've talked about a second ago that, in terms of solubility, it's not 100%. There are a lot of factors that do affect whether or not you would, perhaps see a solid form or not see a solid form. So one such factor that affects whether or not you will see a solid form is common ion effect. And we saw the common ion effect when we were doing buffers, obviously. And it does have the same sort of effect here with solubility. So if we just think about it logically in terms of how the reaction is written, we got our solid on the left, we have our aqueous ions on the right, which means if I had a common ion in here, which side of the equation would it be on, left or right? The only place where we have ions are on the right-hand side, which means in terms of Le Chatelier's principle, we would be adding to the right-hand side, which means it would shift away from it, and that's going to keep it together and be less soluble. So the presence of a common ion in this type of solubility is very much what we see when we talk about buffers and weak acids or weak bases, is going to actually keep the thing together. It's going to lower the solubility of it because Le Chatelier's principle is going to push it back together and stay together. So for example, if we look at silver bromide here in pure water, and the KSP is silver bromide, I'm assuming is that number that popped up there, 7.7 times 10 to the minus 13. If we did our little calculation here, this is our silver bromide, which would break apart into a silver ion and a bromide ion in this case. Our KSP is silver and bromide, and that is going to equal 7.7 times 10 to the minus 13. So doing our ice table here, 0, 0, change plus S means at equilibrium here, we're going to have S and S. That will go into our KSP expression here. That's going to give us S squared is equal to 7.7 times 10 to the minus 13. We're going to square root both sides there, and that's going to give us a molar solubility here of we'll go 8.8 times 10 to the minus 7 moles per liter of silver bromide. just to give us an idea there of the grams per liter. Silver was 107.9, bromine is 7990, and I'm stuck in scientific notation. Now I have an error, which is even worse, I suppose, because I keep hitting the wrong button. Let's try that. Let's go with 187.8, I hope, grams per mole. So basically the solubility here of silver bromide in water is, where'd my number go? Right about there, I think. 0.000165 grams per liter of silver bromide. So once again here, is that a lot? That is not a lot, right? So that's less than, I think, almost silver chloride, if I'm not mistaken. And now what would happen, though, if we put our silver bromide in a solution that also contains sodium bromide? So my sodium bromide is a strong electrolyte, which means when it goes for a swim, it is going to 100% break apart into sodium ion and the bromide ion in this case. So the only thing here that's going to set up an equilibrium is my silver bromide. And again, we'll get our ice table here. Obviously, as you probably can imagine, what we are seeing is the bromide is our common ion in this case. And since this guy's concentration is 0.001 molar, it is a 1-to-1 relationship between those two things. The bromide's concentration is 0.001 molar being supplied by this sodium bromide. So when we go to do our ice table here, just like what we do with common ions or buffers, this is going to be 0, but we are going to have, once again, an initial concentration of the bromide that's going to be supplied by the sodium bromide in this case. Change is going to be plus S and plus S. That means at equilibrium, we have S and 0.001 plus S in this particular case. Just like normal, we're going to, or up here, go into our expression now, and that's going to give us S times 0.001 plus S will equal our KSP of 7.7 times 10 to the minus 13. We know that the KSP is a small value of K, and whenever we have a small value of K, we could do what? We could assume, so in this case, we could actually assume that S is equal to 0. Just like what we do with the X's, we can't get rid of them both. It would just be the one you're going to add to or subtract like we kind of do with the X's. That would then make this guy S times 0.001 is equal to 7.7 times 10 to the minus 13, which obviously I could then divide that guy to the other side. And that's going to get me 7.7 to the minus 13 divided by 0.001. That's going to give me an S here of 7.7 times 10 to the minus 10, and that would be our molar solubility here of our silver bromide in the common ion. Just in comparisons here, we could see this is to the minus 10, and in water it was to the minus 7. It is more soluble in which one? Is more soluble in the water. Yeah, it doesn't have that common ion. Just to give you a gram to gram comparison, it's 187.8 grams per mole. It's the molar mass of silver bromide from the periodic table. Again, I hope that's what it is. And at that point, that's too many zeros for this late hour to read. So that is 1.4, we'll call it there, that's good, times 10 to the minus 7 grams per liter. So that is significantly smaller, right? You can see you could only get 0.00000014 grams of it to dissolve in 1,000 milliliters, basically of water in that case. So that presence of the common ion here is pushing this equilibrium back this way and keeping the solid together and not allowing more of it to dissolve. Any questions on that? Yeah.
And then for the initial, that with BR.
That's let me find somewhere right here, maybe where that's basically how sort of concentration works. So if we had something like say our silver bromide, like we were looking at there, our sodium bromide. And when it breaks apart into Na plus and our Br minus here. And basically, if we have the concentration like we did there, I think it was 0.001, that is moles per liter of sodium bromide. So you could do just like a stoichiometry sort of move, and it is a 1-to-1 relationship between those. And basically what you're doing is for every 1 mole of the whole thing there, you get 1 mole of Br minus, and that is how it stays basically the same concentration for the Br minus. It would also be a 1-to-1 relationship between the sodium if you needed it. Now, if you had something, let's say like calcium chloride, and that broke apart into a calcium ion and 2 chloride ions, and let's just say that the initial concentration of this guy was 0.1 molar. That would be 0.1 moles per liter of calcium chloride. And if we were interested in the chloride, it's a 1-to-2 relationship. So in that case, you basically would go 1 mole of calcium chloride gives you 2 moles of chloride. Those cancel, gives you 0.2 moles per liter of the chloride ions. It's a 1-to-1 for the calcium, so it'd actually be the same. So that's really the long calculation. Of the quick way to do it is you could take the molarity and multiply it by the coefficient. So if you take this guy and multiply it by 2, gives you this. If you take this guy and multiply it by 1, you still get that same number there. And that's the quick way of doing it. But this is really why that works, is basically from this calculation here. Yeah. You're welcome. Other questions? Okay, so one thing that affects obviously the solubility of something is the presence of a common ion. So why don't you give it a go here? The KSP of silver chromate looks like 9 times 10 to minus 12. What would be the solubility of this compound here in a solution that's already 0.1 molar? We'll go with the molar solubility here. How's that? Okay, so let's take a look at this one. So we're looking for the molar solubility here. So we got a little silver chromate. And that is going to break apart into a couple of silver ions and a little chromate action there. It's going to give us a KSP of silver. Again, we do need to square it because of the coefficient, times chromate here. And again, that's going to equal our KSP of 9 times 10 to the minus 12. We're going to roll an ice table here. We do have it in a solution of potassium chromate. So once again here, potassium chromate, a little K2CrO4. That's going to break apart into 2 potassiums and a chromate. In this case, it is 0.1 molar. It is a 1-to-1 between that and the chromate, which means the chromate is also going to be 1 molar in this case. And that is important, obviously, for right about here in our calculation. Again, you do need to make sure you have a number here when you have a common ion. Change going to be plus 2s in this case, and plus s. That means at equilibrium here, 2s and 0.1 plus s. At this point, we're going to go into our expression there. That's going to give us 2s squared times 0.1 plus s is equal to 9 times 10 to the minus 12. We're going to once again assume x is equal to 0. Or s is equal to 0 in this case. By the way, you should check it, but probably in most cases on the KSP, you're going to be in good shape because it's relatively small anyways. That would get us 2s squared times 0.1 equals 9 times 10 to the minus 12. Again, that's 4s squared times 0.1 equals 9 times 10 to the minus 12. So taking my 4 and times it by 0.1 gives me 0.4. And again, we're going to divide that to the other side. So we're taking the 4 and that and taking it to this side. So it's going to be 9 to the minus 12 divided by 0.4 will give me s squared is equal to 2.25 times 10 to the minus 11. A little square root action on both of them there. And going to give us 0.00000. I know I don't feel like scientific notation today. So that is 4.7, and that would be our molar solubility in this particular case here. Obviously, again, if we wanted the grams per liter, we would do the molar mass there of silver chromate in this case. We could check this just to show you again, if you took that number divided by 0.1 and times it by 100, you're nowhere even near 0.1%. So usually, it's a good idea to check it, but usually in these cases, you're going to be probably fairly okay with the assumption. Question on that there. All right, we'll lay it up there for